Hello students, this is Dr. Munir Omar with CS371 Data Communication and Networks. As per our curriculum, today we have lecture number 31 which is about IP version 4 datagram. In this lecture, we will study about all the fields of IP datagram in details. This lecture is divided into two parts. Before starting the IP datagram, let's have a look at the packet encapsulation. So at application layer, we will have data. At transport layer, it would become TCP segment or UDP packets. Here, the TCP or UDP headers are appended with the data. Then at network layer, IP header is attached with this segment or packet, and this becomes IP datagram. Actually, in today's lecture, we will study this IP header. After that, this entire IP datagram is inserted into the network frame, starting with frame header and ending with frame trailer at data link layer. Here we have some sizes, and these sizes are for the headers, for frame header, for IP header, and for TCP or UDP header. So our main concern in today's lecture is IP header. The minimum size for IP header is 20 bytes. This size may be greater than 20 bytes because we have one field known as options. If we use that field, then the IP header's size would be greater than 20 bytes. Internet Protocol IP. It is responsible for end-to-end transmission because in this we use the IP addresses of the sender and the receiver to identify the communicating devices. Sends data in individual packets. The maximum size of packet is determined by the network. If the size is too large, then these packets are fragmented or divided into small parts. The IP is unreliable. In last lecture, we studied about TCP and UDP. So the reliability is actually the responsibility of transport layer, and here in the network layer, IP is not responsible for any reliable communication. So packets might be lost, corrupted, duplicated, and delivered out of order. So these are not the responsibilities of IP. Therefore, IP is unreliable. IP datagram. At network layer, one header is added with the data. This header includes some important fields, and these fields are of different types. Each field has some function or used to identify some sort of information or data. The word size is 32 bits, and there are at least 5 words in a header. We may have option as the sixth word, and beyond option we will have data in the IP datagram. So we have version of 4 bits, then header length of 4 bits, type of service, total length, vacation, flags, fragmentation offset, time to layout, then protocol, header checksum, source and destination IPs, and at the end, options. So we are going to discuss all these in the coming slides in details. First, version, which is of 4 bits. The version is the IP version number. Currently, we are using 4, So its value would be 0100, which identifies 4, and it can also be version 6, which can be identified by 0110. So the possible values for version can be either 100 or 0110. Then we have header length. The header length in 32-bit words. So if the number is 6, if the value of header length is 6, then there would be 6 into 32 bits words in the header, that is 24 bytes. The maximum size is 15 into 32-bit words, which is 60 bytes. And the minimum size is 20 bytes or 5 into 32 bits. So here we have minimum size of 20 bytes and maximum size is 60 bytes. If we include option, then we may have some additional words and that would lead to 60 bytes. Let's consider an example for the header length and version. An IP version 4 packet has arrived with the first 8 bits as shown. First 8 bits. So if you look into the sizes, version has 4 bits and header length has 4 bits. So these 8 bits are for header and for version and for header length. So the first 4 bits would represent the IP version, and here we have 0100, which is representing 4, and then we have 0010. Now it says that the receiver discards the packet. Why? There is an error in this packet. The 4 leftmost bits 0100 show the version, which is 4, IP version 4. The next 4 bits 0010 show an invalid header length. If we look into this number, this number is equal to 2. So the header length would be 2 multiplied by 4, that is 8. 2 multiplied by 32 bits or 2 multiplied by 4 bytes, so it would be 8 bytes. The minimum number of bytes in the header must be 20, as we know. So the packet has been corrupted in the transmission because this too is wrong. It must give us 20 bytes. Example number 2. In an IP version packet, the value of header length is 1000 in binary. How many bytes of options are being carried by this packet? Now here for header length we have 1000. So if we convert this 1000 to decimal, it will give us 8, which means the total number of bytes in the header is 8 multiplied by 4, or we can say 8 multiplied by 32 bits, which is equal to 32 bytes. So the first 20 bytes are the base header. These 20 bytes from here to here, these are the base bytes. Then we have option. So here we have 20 bytes without option. So if we subtract this 20 from 32, we will get 12 bytes for option. So according to this example, here we will have 20 bytes, and then for option we will have 12 bytes. The total would be 32 bytes, and according to header length we are getting 32. 8 bits for service. So the type of service uses 4 flags. The first one is minimize delay. The second one, T, is used to maximize throughput. Then R is used for reliability or maximize the reliability and minimize cost. So we have these 4 type of services. We have also differentiated services in which we use the code point for these bits. If we put zeros to these 4 bits, then it would be a normal case. If we put 1 in the C, then it would minimize the cost. For R, we must have 1 here, so maximize reliability, and for maximize throughput and minimize delay we are also these ones to the flags and zeros to the rest of the bits. The precedence subfield was part of version 4 but never used. So here we have 3 bits for precedence, but these 3 bits are not used in IP version 4 because we don't have any sort of additional flag. Here we have a table showing the default types of services. For example, for ICMP, there is no need of any type of service bit. And if you look into FTP, then we need the throughput primarily. So we are giving bit to T. And if you look into DNS, then we are also in need of throughput. We are giving 1 for throughput. For the code points here, if we are using differentiated services under type of service, so for the code points we have some values here for some protocols. For example, for TCP we must provide 6, which is equivalent to 110. Here we will put 110 in the code point, having differentiated services in the type of service. Now move towards the total length, which has 16 bits or 2 bytes. The total length field defines the total length of the datagram including the header. So this field defines the total length of whole this header plus data, the length of this entire datagram header plus data. An Ethernet frame or the frames which is created at data link layer, we would have a total length of minimum size equal to 46 bytes, and we may need some additional bits for adjusting the word size. Those bits are known as padding bits. So the data bytes would be less than 46 bytes. Let's consider an example. In an IP version 4 packet, the value of header length is 5 and the value of total length field is hexadecimal 28. How many bytes of data are being carried by this packet? First, we must know the size of header. So for that, we must multiply this 5 with 32 bits or 4 bytes. So the header length value is 5, which means the total number of bytes in the header is 5 into 4 bytes equal to 20 bytes. Means there is no option included in the header. So we have 20 bytes for header. The total length is 40 bytes. If we convert this hexadecimal number, it would give us 40. So we have total length equal to 40 bytes, which means the packet is carrying 20 bytes. 40 minus 20. 20 bytes for header and 40 bytes for header plus data. So we will have 20 bytes of data in the IP datagram at network layer, which is passed to detailing layer. Then we have identification, flags, and fragment offset. These three fields are related to the fragmentation of the IP datagram. When the size of the datagram is larger than the underlying network can carry. So these three fields are related to fragmentation, and now we are going to discuss these three fields. First, let's know about the fragmentation. A datagram can travel through different networks. This is obvious that if we have multiple networks, then these networks may exchange data with one another, or the devices or the hosts in these networks may communicate with one another. Each router encapsulate the IP datagram from the frame it receives, process it, and then encapsulates it in another frame. The format and size of the received frame depend on the protocol used by the physical network through which the frame has just traveled. In simple words, we can say that if there are different networks, then these networks may have different sizes for frames. The format and size of the send frame depend on the protocol used by the physical network through which the frame is going to travel. For example, a router connects a LAN to a WAN. So it receives a frame in the LAN format and sends a frame in the WAN format. So this is obvious that the sizes at LAN and WAN would be different. So the router has to fragment, has to divide the frame into small pieces or to make more frames so that it becomes acceptable by the other network, or in reverse assembly multiple frames into a bigger frame so that that new frame can be adjusted in the connected network. In the second word, the first field is identification, which has 16 bits. The identification is a unique number assigned to a datagram fragment to help the reassembly of fragment datagrams. Actually, it is obvious that these datagrams are fragmented or divided into several pieces. So, this identification is used to identify each fragment. Each fragment is given a unique number. Here we have 16 bits or a we have 16 bits or 2 bytes. So the maximum number for identification can be 65,535 or 2 power 16. So we can identify around 65,000 fragments. So this is a big number for fragmented datagrams. Then we have flags. We have 3 bits for flags. Bit 0 is always 0 and is reserved. Bit 1 indicates whether a datagram can be fragmented or not. So first 0 bit would be 0, then second bit would be either 0 or 1. If it is 0, then it means that the datagram can be fragmented, and if the second bit is 1, then we will say that this datagram cannot be fragmented. Bit 2, the third bit, indicates the receiving unit, whether the fragment is the last one in the datagram. So if the last bit in these 3 bits, if the last bit is on, means it has 1, then it would indicate that the fragment is the last one in the datagram. And if there are more fragments to come, then the last bit would be 0. For example, here we have 0, 1, and 0. So this would mean that this fragment cannot be, so this datagram cannot be fragmented. Now if we have 0, 0, and 1, it would mean that the existing fragment is the last fragment. Now if we get 0, 0, and 0, then it would mean that the IP datagram can be fragmented, and this one is not the last fragment. The next field is fragmentation offset. Fragmentation offset in unit of 8 octets or 16